This is section 2.2, and what we begin with are linear transformations. And now, this is an interesting thing. Let me toss in three words here: function, transformation, and the third one, let's do mapping. Actually, these are all synonyms. Synonyms. Is that right? Synonyms? Looks funny to me, but anyway, so with these three things, you know, if somebody says, oh, it's a transformation, well, then it's a function. Oh, it's a mapping. Well, then it's a transformation or a function, or, you know, if it's a function, oh, well, it's a transformation or a mapping. I mean, they truly are synonyms. Kind of why, though, all of a sudden, why do they say linear transformations as opposed to just linear functions? Why are they throwing new words in here? Well, there is a little, you know, some subtle differences in context. Typically, when we think of transformations, often we're maybe thinking that it preserves particular algebraic properties. So that may be the case why we use transformation. Definitely in linear transformation, that is something that it does, and we'll see that in a minute. Oops, I forgot properties there. Or, you know, maybe it has some geometric aspect. Geometric, there we go, aspect. And so maybe that's what's going on. So perhaps it preserves the general shape, or it preserves distances, or it preserves area, you know, things like that. So you'll tend to see the word transformation used then. And so we're looking at a linear transformation. And so we'll say, okay, T from, and often, I guess, because it's, you know, may have some geometric aspect, something like that, often it will be a function that goes from whatever set it's talking about to another set or something like that. Now your textbook, they use for their set, they'll say, okay, it goes from f sub n to f, not sub n, super n, f super n to f super m. Now, you know, why these f's? Well, these are, you know, the author likes to talk about fields and so forth. So typically for us, you know, this f super n and f super m, and also for this author, in this course anyway, they're just going to be n-dimensional space, so n-dimensional vectors, or m-dimensional vectors, okay? And in the textbook, they toss a small a down here. And so I'm going to say this a little more generally, though, and so I'm going to say that TA from Fn to Fm is a linear transformation. Okay, oops, running out of room there. We'll put it down here, linear transformation. Okay, if for some x in f in, and actually I should really, we want to get used to notations and that sort of thing. So an element of, if it's in there, so if it's an element of f in, then what we have is that if I took TA of, so here's the function idea, Sx plus, oh, so really they use an x and a y, so I'm kind of looking at what they have. So let me, I was going to do it slightly differently, and then, but I'll try to mimic what the book has here. So x and y in Fn, and then t times y. That is the same thing as s times t a of x plus t of ta of y. And so there were two things that happened there. We had scalar multiplication come out. So we had ta of sx is just s ta of x. And we had addition that could be brought out outside of this function. And so if we had x plus y here, then that's ta of x plus ta of y. Now, they immediately just go to matrices, but what I'd like to show you is that other things can be linear transformations. Okay, so for instance, okay, so not matrix stuff. I'll just show this one example just to show that, you know, this is way bigger than the matrices, but the nifty thing is that all these linear transformations actually can be represented by matrices. So that's one good reason to spend a lot of time, well, on what we call finite vector spaces. Okay, so we can represent those by matrices. So not matrix stuff. Well, suppose what we have is I want to define my transformation, and I'll keep the A there. Now, they use the A for a matrix A, but suppose I have TA, and I'm going to take that from what we call, well, let's see, what we could call, and I'm going to use a lowercase f, f1 to the real numbers. And in this f1, actually I could call it f0, okay, continuous functions from, so I'm going to have a transformation that goes from continuous functions to the real numbers. And what that's going to be is defined as ta of some function f of x is just the definite integral from 0 to 1 of f of x dx. And so that's my transformation. And you see, I'm going from the space of continuous functions on the interval 0, 1 to the real numbers, because if this is a definite integral, I get an answer. And that's a real number. But notice, right, that if I take two functions and I want t of a, say some s times f of x plus t times g of x, right, that's going to be the integral from 0 to 1 of this whole thing, s f of x plus t g of x dx. But then that is, I can separate the integral at the plus, so this is the integral from 0 to 1 of s f of x dx plus the integral from 0 to 1 of t g of x dx. And then I can pull out the s and the t out of each of those integrals because they're just real numbers. F of x dx plus t times the integral from 0 to 1 of g of x dx. But you see, that's just s times ta of f of x plus t times ta of g of x. So it's a linear transformation. So we're going to be talking about matrices, but it's bigger than that. Okay, so I just think it's very important to realize that some of these things are much bigger in mathematics than what you might learn in one particular class, and so you know, we want to I guess realize that, you know. So why linear algebra? Well, my personal opinion is that linear algebra is really so much at the root of almost everything. I think it's one of the most important courses one can learn, even if mostly what you work with is matrices. Because if you really get this idea of linear transformation, and we do it with matrices and so forth, then you know, going to, you know, sort of branching out and realizing that, oh, okay, the set of functions that are integrable, you know, continuous functions integrable on 0, 1, you know, that we could think of kind of like we think of current vectors right now that we have. So, you know, and then some of this stuff working with those functions and so forth is much easier because all of a sudden I can put it in context of the stuff I know from linear algebra. And so anyway, there's an example of a linear transformation that at least, you know, here, definitely as we look at it, seems to have absolutely nothing to do with a matrix. But again, if we're doing this over finite things, then turns out you can represent them with matrices. And there's another good reason, though, to be studying matrices. Okay, so let's get back to matrices. And, you know, so suppose I have TA goes from, and I'm going to call it Rn to Rm. And so all that means is a vector of size n or a vector of size m. And the way we'll do this, actually, I'm going to go from Rm to Rn. I'm going to switch those around so it fits our matrix, right? So if that's what I want to do, then I'm sorry, got myself backwards. No, that's what we do want to do. This will happen. Sorry, mostly it just makes you have to sit through a little more video or something, but sorry about that. So yeah, we do want to go from Rn to Rm. And the way we'll do it is then for x in, and I'm going to put a line over it now because I'm definitely thinking of it as a vector. For x in, for x, whoops, in, let me try that again. For x in Rn, TA of x, we're just going to define it as AX, and that is going to be in Rm. And so what that means is A is m by n, right? M rows, okay, because x here, this original x is n rows, right? So this original x is n rows. It gets multiplied by a m by n, and I can do that because if x has n rows and a has n columns, I can do that multiplication right there. And then, though, the result will be m rows. Okay, so a is just m by n. And that is the definition of our linear transformation. And we can check that from our properties of matrices that certainly that's a linear transformation. Because if I take TA of s times x plus t times some y, then according to this is a times s x plus t y. But our properties of matrices say I can distribute that matrix multiplication over the addition. So I get a times asx and a times aty. And then the scalar, again, by our properties, I can write that as s ax like that and t ay like that, but now that's s times ta of x plus t times ta of y. So it's a linear transformation. Okay, and so there we define our linear transformations, and now we'll make some videos where we just kind of look at some various examples. Most of the examples in this text are geometric in nature. Okay, so linear transformations.